Welcome to the video on half-life. This is a very simple concept. Once you've got first order reactions and second order reactions figured out, this follows right along with them. Definition of half-life: the amount of time required for half the reactants to turn into products. Now, typically people are introduced to the concept of half-life in regard to radioactive substances. And then the half-life is how long it takes for half of the amount of substance to decay into whatever new element it's going to become. And that is true. But we can also talk about half-lives with any reaction at all. Anytime reactants move to products, how long does it take for half of that to occur would be the half-life for that reaction. So it can happen with normal reactions also. We have already discussed first-order reactions and second-order reactions. They are radically different when it comes to half-life. For a first-order reaction, the half-life is always constant, meaning if it takes 10 days for the first half to decay, it will take 10 days for another half to decay. So by 20 days, you'll be down to a quarter of your original material, and it'll take another 10 days to get down to an eighth, and so on and so forth. All radioactive material is a first-order reaction. So all radioactive decay is a first-order reaction with a constant half-life. And that's how they can use radioactive decay to date things. Depending on how long they're dating, they use different material. So basically, when you have radioactive decay, you're talking about one substance all by itself turning into another substance. So there is no other thing involved, therefore it would have a first-order reaction. Second-order half-life is kind of weird because the half-life will change throughout the course of the reaction. It depends on your starting concentrations. So let's look at a couple of tables to compare here. Let's say we had a first-order reaction. And we're going to measure this reaction every 10 minutes and see what the concentration is of our substance. So at 0 minutes, we start off with 0.1 molarity. And then so on and so forth. It constantly goes down until we're left with hardly any reactants, mostly products. To figure out what the half-life is, you take your starting amount and find where on this list of concentrations is half of that amount. So I say, okay, if I'm starting off with 0.1, then half of that would be 0.05, and that is here. Now you'll notice that it took 20 minutes to get half decayed, so we should expect for a first-order reaction, for another 20 minutes, another half will be decayed. So if we look at 20 minutes later, that's 40. Yes, it is about half. Now you're going to notice that these tables, because they're experimental data, aren't going to come out exactly perfectly, so I tried to replicate that here. But it's about half, and again, if we look 20 minutes later, it's about half again. So every 20 minutes, you're losing half of your reactants. That is what happens in a first-order reaction. Let's look at what happens in the second-order reaction. So again, we're going to measure every 10 minutes, and we're going to measure concentrations. Again, we're starting off with 0.1 molarity of our reactants. And so we look for half, and we see, okay, from 0.1 to 0.05, that's, again, 20 minutes. So we say, okay, well, what happens after another 20 minutes? Well, we go down to here, 0.035 is not half of 0.05. It takes a lot longer to get to another half, and it's like not even on this chart, okay? So it'd be like 80 minutes or something like that. So if you are trying to figure out, looking at tables like this on a test, whether you're looking at a first-order reaction or a second-order reaction, find half, and then find half again, and if it's the same amount of time between those halves, then you've got a first-order reaction. If it's not the same amount of time, it's longer or shorter, then you have a second-order reaction. And I believe it should be longer. If you, and that is 90% of the time, if you're talking about half-lives and second-order reactions, this is what you're dealing with. They're just going to give you a table of time and concentrations and ask you, is this a first-order reaction or a second-order reaction? And that's how you figure it out. Now, let's say that you have a first-order reaction, and it's asking for the half-life. And instead of giving you times and table like that, where you just find how long it takes for you to go half, they're giving you a rate law. So we have this reaction A to B, and we've already discovered that the rate constant is 0.3 inverse seconds. What can we do to find out half-law? Well, remember the first-order reaction equation. Can you remember that already? Natural log of the concentration at time equals T minus natural log of the concentration of time equals 0 equals negative kT. And again, we want to know what is this at half-life. So that means we need to fill in these values. You're just like, well, I don't have a table. Like, that's what we've done in class so far, is we looked at tables and we filled in values from the tables. So if I have no values, how am I going to solve this? All I know is K. You don't need values for half-life because you know it's half. So whatever this value is, what your starting value is, just take half of that for this. It doesn't matter what it is. As long as it's first order reaction, it doesn't matter what the concentrations are. Only for the second order reaction would it matter. So the easiest thing to do is to say we start off with 1 molar. That means that at half-life, we're going to have half a molar. So then it's the natural log of half minus natural log of 1 is negative kT. And we know that K is 0.3, so let's just go ahead and put that in. Negative 0.3 inverse seconds. Well, everybody should know, hopefully, that you can just put this in the calculator. So if we take the natural log of 0.5 minus natural log of 1, we get negative 0.693 equals negative 0.3 T. And so then we can divide both sides, 0.3, and figure out what the half-life will be. So for this particular example, 0.693 divided by 0.3 is 2.31. So it'll take 2.31 seconds for the time. And now I probably should have given you some more sig figs here so that we don't have an unreasonable number of sig figs, but it'll be 2 seconds if we run out of sig figs. So you can just find half-life of any first order reaction if you just substitute in numbers like 1.5. It would have worked out perfectly if we had substituted in, or we would have done 2 and 1. It doesn't matter. If you want to try that out, just prove it for yourself, you can, but you still get the same answer. So if it's the same way all the time, there is another way to do this. So we found that this equals negative 0.693. We could just say that the half-life equals negative 0.693 divided by K, whatever K is for that reaction. So that's the half-life equation. If you forget that equation, don't worry about it, because you can just use logic to go back and here's the equation you do remember and figure it out again. But if you want to, you can just memorize that equation. All you need to know is K, and you can find the half-life. And we've talked about many times how you can find K depending on different information they give you. They give you K, we find it from the slope of the line, etc., etc. So that is half-life in a nutshell. First order half-life, first order reaction half-life is far more common of a question than second order. If it's second order, it'll probably just be, how can you tell whether this is first order? Thank you.